This is 6.1.2. Let's overview the different types of Fourier transform. In the previous part 1 of this lecture series, we dealt with continuous time signals, and continuous time signals has continuous time Fourier series and Fourier transform. And continuous time Fourier series can deal with periodic signal. When you want to deal with not periodic signal, we have to use continuous time Fourier transform. Actually, continuous time Fourier transform can also deal with periodic signal. So we draw the signal x of t here, which is the periodic signal with the little tilde on top to show that it is repeating, time is continuous. And aperiodic signal, we draw a square pulse, singular square pulse to represent it. Here, these are just examples of possible signals. What about discrete time? So discrete time basically says that we sampled the signal, and then now it becomes a sampled sequence in time. And when we sample the signal, whatever it is between here is not defined. It is not zero. It is just not defined. So let's sample the signal, and when we sample the periodic signal here to here, it remains periodic if, or I should say, it remains periodic under some conditions. So you must be very careful. A periodic signal in continuous time does not necessarily becomes periodic. Okay, but let's say in this example, we have a 5 sample periodic. That means xn equals to xn plus 5. So after 5 signal, it repeats itself. Again, we can use DTFS, discrete time Fourier series, or discrete time Fourier transform to analyze this. We also have, when the signal is aperiodic, so it's 1 1 at these 2 times and all zeros. So now there's no period. There's no xn equals to xn plus small n plus big N. In this particular case, we're left to deal with discrete time Fourier transform. Now, lastly, you realize that if you have a signal that, for example, in this signal xn is the same as the top signal for this first 5, but after that it is different from x6 onwards, and it is different also from x minus 1 onwards. So how do we deal with this signal? Well, let's say that we are only going to restrict our attention or analysis to these 5 signals. Then you realize that you can take the DTFS, which is this guy, on this signal and pretend that it's periodic. That's what DFT is doing. So DFT is analyzing a signal only at a fixed interval, 0 to 5, 0 to 4 in this case. And outside of it, it doesn't know what's happening, and you cannot tell, and it cannot tell. And this is the DFT analysis. Okay, so we'll come to, in this part of the lectures, we'll deal first with discrete time Fourier series and Fourier transform, and in the last part we'll deal with DFT. Here are the equations for the analysis and the synthesis. What does the analysis means? The analysis takes the input signal x of t and generates the coefficients representing x of t in the frequency domain. We have x of t here and becomes x of omega because this is the continuous time Fourier transform. And in the continuous time Fourier series, it is a of k, where k represents the kth harmonic. So later on you realize that k here is k omega naught, where omega naught is the fundamental frequency. Analysis breaks the signal in time into the frequency representation. What about synthesis? Synthesis takes the representation in the frequency and convert it back to time. Similarly, because AK is not continuous, we have A1, A2, A3, A4, and in fact we have A0 as well as A minus 1, A minus 2. We use a summation to act on all these A's and multiply them with e.g. omega k times omega naught t to reconstruct x of t. So in fact, the synthesis equation tells you what exactly Fourier transform is. Fourier transform breaks down xt into different a's, and the different a's tell you how much contribution it has on the original xt. Now, when we are in continuous time Fourier transform, the representation is continuous. It needs all the frequency. So omega here is continuous. It needs all the frequencies, and hence instead of a summation, the integral is being used. So this is continuous time Fourier series and Fourier transform. Similarly, for discrete time Fourier series Fourier transform, these are the equations. In the analysis, typically the notation used is ck instead of ak. And what we deal with is that if we have n samples of them, for example, in this example, we have 5 samples, then we only need to look at these 5 samples from n0 to n-1, the first period. We take the input signal x of n, and to analyze it, we actually introduce this function, which is nothing but a dot product between xn and this complex exponential with 5 samples. So discrete time Fourier series takes the input signal, uses this equation, and convert it into different coefficients. Different coefficients arise because we have different harmonics acting on this dot product. So we have C0, C1, C2, until actually, because there's only n samples, we only have C0 up to Cn-1. Now, once you have analyzed this, the ck represents the signal xn in the frequencies domain. The frequencies are k omega naught. So very similar idea to the continuous time. Later on, you'll realize that this 2 pi over n, to distinguish from the continuous time, we'll use big omega naught, which is 2 pi divided by n. Now, when we have the representation in the frequency ck's, we can use it to reconstruct xn again. To reconstruct, we use this equation. We take the ck, which ck's exists from k equals to 0 to n-1 only. We take ck's and multiply with this complex exponential at different frequencies. So ck or c1 will act on ej1 2 pi over n times n. c2 will act on the second harmonic. c3 will act on the third harmonic. You need to use up to k equals to 0 to n-1 harmonic to reconstruct xn. So this equation is for discrete time Fourier series. This is the analysis equation. This is the synthesis equation. What about discrete time Fourier transform? Well, this signal is aperiodic. Since it's aperiodic, we cannot use n equals to 0 to n, big n-1, because there is no big n, that is the period. So instead, we have to deal with the entire signal from n equals to minus infinity to infinity. Now, of course, if this signal cannot be summed by this expression, then x omega does not exist. So we are trying to add infinite numbers of signals, xn multiplied by e minus j omega n. And sometimes it will not converge. And if it does not converge, it means that discrete time Fourier transform does not exist. But in this very simple case, we only have 1, 1 at time equals to n equals to 0 to 1. So this actually infinite sum actually is only summing across these 2 points, because the rest is 0 multiplying by this guy anyway. So of course it will exist. So in this particular case, when we analyze xn, although of these 2 points, we must use all of omega. What is omega? Here omega is from 0 to 2 pi typically, or minus pi to pi, up to you. But omega is real frequency. It means that it has, up to infinite precision if you are allowed. So typically we'll work from 0 to 2 pi at very fine interval, maybe 0.01 pi, and then we'll substitute different omega, and we'll work out this expression, and we'll have x omega. X omega represents this signal in the frequency domain. And then once we have x omega, then we can reconstruct it. And then to reconstruct xn, we have, because x omega is continuous, we have to do the integral instead of the summation. and then we'll integrate x omega e now plus j omega n d omega divided by 2 pi, and we'll get x of n. Right, finally, in the DFT, what is the difference between DFT and the above? The first idea is that the DFT is also aperiodic. However, let us now fix an analysis window, and we say that we're going to analyze 5 samples. So it's very similar to these 5 samples actually. In fact, it's identical. Outside this window is not the same as the periodic signal. But what we're going to do, we're going to use the same 5 samples. In fact, we're going to use the same equation, almost the same equation as DTFS. The only difference is that the scaling factor 1 over n is not here. So in fact, x of k, which is the DFT of x of n on this 5 sample, is the same as ck except 1 over n. You realize that this 1 over n then appears at this side, and the reconstruction, the synthesis equation is almost identical. See, ck times e plus j 2 pi over n times nk, and here is also xk times ej k 2 pi over n, and the 1 over n comes out. So in fact, you realize that DFT and DTFS are identical. You'll produce identical result with the scaling difference, that's all. In the later chapter, we'll tell you exactly how to manage DFT, because outside these 5 samples, they are not the same as the periodic signal. That's the key idea. So in this one slide, we went through all the equations of continuous time Fourier series Fourier transform, as well as discrete time Fourier series Fourier transform, and DFT. The last takeaway is that all these equations of Fourier series and Fourier transform have no standard notations. Sometimes they use small omega, sometimes they use big omega, sometimes the 1 over n is 1 over square root n, so that it will distribute to the other side. So the idea is that you have to look at the lecture notes or your respective book carefully to see their notation before you use and interpret the representation. Thank you.